panel addresses spectrum sharing in space. The moderator for this panel is Scott Palo. Scott is a professor of aerospace engineering at the University of Colorado Boulder and the associate director of SpectrumX. You can find a full biography of Scott on the conference webpage. So Scott, over to you and your panel. Thank you.
Great, thanks Keith. Just want to make sure we can hear okay, get a tech check. Great, and looks like we have our panelists coming on. If the panelists are available to turn on their cameras to join us. Great, well, looks like we have all the panelists here and have their cameras on. So I want to thank the ambassador for a great overview and background as we set up here for our first panel discussion entitled Sharing at the Final Frontier, Spectrum in Space. And we're going to focus on issues associated with spectrum management of space-based systems and touch on a number of topics related to space-based systems and spectrum. I wanted to take a moment to introduce our panelists really briefly. Their full bios are available online, but to give you some insight to the power and background and intellectual knowledge of the problem that we have here on the panel. So our first panelist is Alexandre Vallet. He is the chief of the Space Services Department in the Radiocommunications Bureau at the International Telecommunications Union. And prior to that, he was head of regulatory affairs and spectrum orbit resources department at the French agency in charge of radio spectrum management. So thanks for joining us. Second, we have David Goldman. David is director of satellite policy for SpaceX. He was the chief counsel for communications and for the Communications and Technology Subcommittee. And before that, he served as senior legal advisor for FCC then Commissioner Jessica Rosenworcel. We have Ashley Vanderley, and Ashley is the senior advisor for facilities in the Division of Astronomical Sciences in the Directorate of Mathematical and Physical Sciences at the National Science Foundation. Ashley represents NSF on the NTIA Interagency Radio Advisory Council, IRAC, and its subcommittees, and serves as U.S. head of delegation on behalf of the State Department to the Radio Astronomy Working Party 7D of the International Telecommunications Union. And we have Peter Tenhula. Peter recently retired with 25 years service at the National Telecommunications and Information Administration as the Deputy Associate Administrator in NTIA's Office of Spectrum Management. And Peter also chaired the Interdepartmental Radio Advisory Committee, or IRAC. So thank you all for joining, and we'll go ahead and get started with some questions. And the first question I wanted to address to Peter. And so Peter, there are a wide range of ongoing space and terrestrial spectrum challenges. The most notable being the GPS legato conflict that regularly shows up in the news. Others include spectrum frontiers and the use of spectrum bands above 24 gigahertz for mobile radio services. From your prior NTIA experience, can you comment on the most relevant domestic spectrum challenges with respect to sharing spectrum between space and terrestrial users?
Sure, Scott, thank you. Thanks for having me. I'm coming to you from the moon. Actually, I'm in a conference room here at the law school at Silicon Flatirons. On your question, a couple things coming to mind in addition to the ones you mentioned. About 4 current battles going on between the challenges, involving domestic and space-based services. And they typically, just to generalize a little bit, is that you look at them kind of like as, are you talking about new entrants versus incumbents, or are you talking about a new entrant and a new entrants and other new entrants, that are trying to develop, spectrum, some on Earth and some in space. because technology is changing all the time. I think Grace mentioned that in her talk about how, technology's probably faster than what the regulation. So, and when I was at the NTIA, we came across all kinds of conflicts. And when I was at the FCC as well, all kinds of various conflicts between the terrestrial side and the satellite side. The dynamics kind of varied, and there was sometimes distortions, in the way that, you had to deal with these battles. It's like Grace mentioned, what is the highest and best valued use of a particular piece of spectrum, and how do you pick between, kind of, and do you choose between winners and losers in that? And and you're talking sometimes you're talking about inside a band, in a particular band, and sometimes you're talking about adjacent band. But let me just run through a few examples. Start with the obvious one, is the L band, which is GPS and legato. And there you've got players with different postures. You got a lot of government users and non-government users of GPS, and no real central arbiter or representative of them to deal with that. And so you got FCC and NTIA kind of representing the various interests, and NTIA and FCC did not agree on the outcome of that. And that involves, a new entrant coming in to want to provide terrestrial service, and what are the potential effects to the satellite service in adjacent bands. And you have different dynamics involving the players there. And it's not unlike, terrestrial, other, kind of battles in just the terrestrial space. In the C band, you had a little more, I think, cooperation, because that was an in-band kind of situation, and that involved terrestrial mobile versus incumbent, new terrestrial mobile versus incumbent satellite. And that seemed to work out well. I mean, there's obviously folks that were disappointed, but there were some meetings of the mind. The decisions moved pretty quickly. There's still some issues above 4.2 gigahertz in that band with the aviation side of things. I'll call that space, since it's up in the air. But the satellite folks had been there a long time with their earth stations, and they realized that they could probably be more efficient, in using that spectrum, and could make room for the terrestrial mobile. In 12 gigahertz, there's an ongoing battle I'll call it an in-band battle between new entrants on the terrestrial side who want to provide mobile service, and the incumbents being the direct broadcast satellite. And there's also a new entrant component to that. So, in that, but in these cases, they require the technical folks to have meetings of the mind, and like Grace said, some level of trust, so that the information the studies that are being provided to the regulators, who are often not that very technically savvy, are understandable and have credibility. Grace was involved. I don't think she mentioned the 24 gigahertz one, but that ended up getting resolved, on an international stage. Lots of conflict internally within the US, and it's a subject of a recent GAO report about how the conflict was handled or was not handled, domestically. So we need a way to figure out to develop trust, especially on the technical side, and that's a challenge. And also to make it understandable to various levels, especially on the political side, because oftentimes there's distortions in these battles. When the political folks get involved, because you need to explain things to them, and you got so it's important to bring, I think, kind of multidisciplinary group together, and kind of negotiate in good faith on the basic engineering terms, and what are the assumptions that you're making. So that's the biggest challenge I see. Did I hit all my examples? I think I did.
Yeah, no,
Yeah.
that's
Yeah.
great. Thanks for that insight. I want to ask, excuse me, if any of the panelists wanted to follow up or have any additional comments on that. Just go ahead and raise your hand in the raise hand button down at the bottom, or as we're going through any of the discussions, if you want to chime in, absolutely, I can, I'll call on you and we can have a discussion. I think it's a little bit more challenging to manage the discussions here in the remote environment. So with that respect, did anybody have any additional comments to follow up on what Pete mentioned with regards to the ongoing sharing, I would say domestic sharing? Yeah, Alexandre.
Yes, thank you, Scott. Just to add that the 12 gigahertz issue that Peter mentioned is specifically interesting because it's not simply a new entrant on the terrestrial side versus an incumbent in the DTH market. And it's also that there is a third new entrant, which are the NGNSO constellations, which also use these bands and which in fact add another layer and another kind of service in addition to the traditional DTH service. So it is really, in fact, three actors on this field, and this makes, in my view, this case very interesting because there will be I'm not so sure that it's possible to share between the three of them. Probably two of them can coexist, but three of them it may be a little bit difficult. So the proceeding will certainly be interesting for this from this point of view. Thanks.
Thanks. I guess and also wanted for the audience to explain that NGSO, for those that are not familiar, is a non-geostationary orbiting spacecraft. So these are spacecraft that orbit the Earth every 90 minutes. Versus geosynchronous spacecraft that largely sit in one location geographically above the Earth. So the non-geosynchronous or NGSO spacecrafts are far more dynamic with that respect. Yes, David.
Hey, yeah, thank you. I feel like, so first let me thank you for including me and inviting me. This is great. I'm really excited about it. I feel like I have to speak up now as one of the NGSOs that's using the 12 gigahertz band. I think that's why Peter raised it, was just to bait me to get involved in it. But yeah, and just real quick, so I work at SpaceX and we operate one of the NGSOs. And so really one of the key differences, just to kind of expand a little bit more on that issue, is that geostationary satellites, it turns out that like the movement of the satellite actually has to do with the altitude you're at. So in order to be geostationary and stay at one point relative to to where you are over the Earth, you have to be really, really far from the Earth. And if you move closer to the Earth, there's a lot of advantages to that because you can get lower latency, and so you speed things up. But the problem is you need a lot more satellites in order to be able to do it, because they do, as you move closer to the Earth, the satellites move across the sky relative to the Earth. So it does, as has been described, it becomes much more dynamic, and there's a lot more issues to it. In the 12 gigahertz band, it actually is an intensively shared band already. Because there's not only, one of the things that I think gets lost a lot when we talk about spectrum is people are very used to terrestrial spectrum and terrestrial spectrum assignments, which tend to be exclusive. For satellite uses, it is all shared. Satellite bands, I can't say that every satellite band is, but at least a lot of the bulk of the ones, and certainly the NGSO ones, are all shared among different operators. So this band is shared, 12 gigahertz is already shared across 3 different technologies, different services. So there's already a terrestrial service called MVDDS. There's the geosynchronous satellites, so the ones that are really far from the Earth, and they're doing satellite television. And then there's several NGSOs in there already. So this band is already shared across 3 different industries, and within each of those industries, a number of different operators. So what the dynamic is there is the terrestrial operators are asking to expand their rights. So this is a shared band where we're actually, instead of going towards sharing, it's The discussion is, do we move away from sharing and do we expand the rights of the terrestrial operators in there? Whereas I will tell you, like from our perspective, we operate below the noise floor. Like in order to be able to share and accommodate, the rules are already so tight in this band that we have to operate at such low power that if you increase the power of other systems, that it necessarily basically breaks our link. And so you can't connect anymore. And so the discussion in 12 gigahertz, I'm not sure it's exactly the way that Peter described it. And again, he's probably just baiting me anyway, but it's because this is a band where you have a ton of different operators doing different technologies, different services. And the question is, can we give more rights to one of them? And how much harm do then we cause to the other services in order to be able to do that? Yeah, I mean, we shouldn't take it over on that, but I think that one has particularly, I actually don't think this one fits cleanly into the dynamics of other bands where it is necessarily a new entrant versus an incumbent. I think there's a lot moving in this one.
Yeah, and I will say that, I'm coming from a technical side in engineering and learning a lot more about policy over time. And the more I peel back the onion, I keep finding there's more movement in all these places than I anticipate. The complexity, I always find surprising as I learn more about the issues. Ashley, did you want to comment on that? I do have a question for you, so I'll move into my question after you make your comment.
Yeah, so a very brief comment. I wanted to add one angle of complication to this as we talk about incumbents. And there's a little bit of a difference here between rights of protection to transmit and the idea of sort of rights of transmission. And I bring this up because the original space-based system is actually nature. So I did want to highlight for those folks who think about it, that nature is always transmitting, right? The sun is transmitting at all kinds of frequencies, stars and satellites are, and galaxies, the atmosphere is. And these transmissions don't require a FCC license to be able to transmit. They're always going to be transmitting whether or not we want them to. And so that's something I wanted to highlight, that scientists have sort of rights of protection, so to speak, in certain bands that have been identified to be the most important for science. But irregardless of that, scientists are always looking to glean information. And so it's also important to just note kind of across the frequency bands that scientists are going to be looking to glean as much information as they can where nature is choosing to transmit. So that's something to kind of keep in the back of your mind all the time. And this is especially important as we think about things like solar flares that can have an impact on our commercial space system. So I did want to just raise that point.
That's a great lead in. So I wanted to ask, so Ashley, you've been involved in the scientific use of radio spectrum for many years as an astronomer, and more recently as a senior advisor at the National Science Foundation. The radio spectrum is critical for a myriad of scientific applications, including weather forecasting and scientific exploration, such as radio astronomy. So I wanted to ask, from your perspective, what is the rapid growth of commercial space systems on scientific users? And also, what do you see as the opportunity and challenges for sharing as these systems evolve and expand?
Yeah, that's a great question, Scott. And I think, as Grace mentioned in her keynote, advanced sharing technologies and really driving on the research and development and innovation is going to be the key as we move forward. And that's kind of part of what's motivated NSF to establish the Spectrum Innovation Initiative and really try to drive research dollars towards that. The question if there's an impact, hopefully I can describe, very quickly. Yes, there's an impact, but it's not necessarily all negative. And it really depends on, what angle you're coming from. As Grace mentioned, what is the highest and best use? It really depends what your mission is. So I wanted to emphasize the fact that, here we're really all are on the same team, right? So we're trying to, at least from the scientific perspective, glean that knowledge that is going to be useful to benefit even commercial systems. So Scott, you're really familiar with CubeSat. So this is a great example of a research area that NSF has funded. And so NSF CubeSats in low Earth orbit, one of their main missions is to understand the space environment. So they make in situ measurements, they do remote sensing to better understand the atmosphere. And this is going to lead to an understanding of propagation that's coming from, the broadband signals being transmitted either at that same orbital altitude or higher, and things like drag that are going to be important for recommendations like the 25-year deorbit. So, that research and information is really helpful to contribute back. And so this is where science is not really just the purview of scientists. This should be knowledge and information that all of us are learning and sharing with each other, which is the scientific process. The other point I wanted to kind of make related to impact is, highlighting that there are different needs, different tensions and stakeholders. And so this can really complicate, how you evaluate and how you make decisions. And you really want to do it thoughtfully and carefully. So 2 quick examples there. I think one, atmospheric water vapor is a great example. If you think about radio astronomy from the ground, they actually choose bands to observe, atmospheric and effects in the universe based on where there's not water vapor. And so, for example, 86 to 115 gigahertz is a very transparent window. When you get above 116 gigahertz, you have a water vapor line. So it's not really a useful band per se for most ground-based astronomy unless you're on a very high mountain without a lot of atmosphere above you. Same with 24 gigahertz. But those bands are very valuable, as you know, for atmospheric scientists. They're going to use that for climate and weather modeling. So you see, even in the science perspective, there's not a common view on what band matters the most. It really depends what you're trying to study. Another example, I was really glad that Peter brought up on the global navigation system and GPS, global positioning system that the US runs, because I think this is just another example to really illustrate impacts of commercial systems and the fact that there's kind of this very dynamic system. So when GPS was launched, around 1500 megahertz, 1200 megahertz, huge impact, negative impact to radio astronomy. So they do a lot of observations from 1 to 2 gigahertz, only protection in a couple little bands that are the most critical. But wherever these GPS signals are, it's not possible to glean that really faint information from the universe anymore, from a distant galaxy. So astronomers have to just, cut that piece of the band out of their data, and they can't glean that information. So a negative impact, you would say, to scientists' ability to study the universe. At the same time, however, though, radio astronomy provides really useful information to global navigation by providing the most precise Earth orientation. So the Earth is constantly moving, stars are moving, and so we need to know where the Earth is and where the satellites are for things like traffic management. And so radio astronomy, by observing very distant galaxies and quasars, can provide that information that is very useful for the commercial space sector. So you see the positive and negative coming from the radio astronomy service in this. Now add on to that a layer that atmospheric scientists actually use these really bright signals to look at radio occultation, and they're able to do profiles through the atmosphere. And this is really great information for climate change, weather monitoring, etc. So something that has caused, a negative impact to radio astronomy has led to creative and beneficial scientific studies by atmospheric scientists. So I just bring this up to say, as we work, moving into the future with, these new mega constellations of satellites, lots of challenges. We've been working very hard with SpaceX and other companies to find ways of mitigating challenges to certain science cases, but there's also, potential opportunities as well. And so this is where I think, this open dialogue and conversation about what is it you're trying to accomplish, how can we work together? And then as Grace mentioned, really thinking about where do we want to be 50 years from now, and how can we, fund the research and the innovation that we need to get there is really going to be the best approach, because there's, great good that comes from all of these different services. And so we just have to, understand each other and try to work through that. So those are just 2 quick examples, but yeah, great question and really complicated.
And I think that follows up on a point that Peter made was understanding each other and developing trust. I mean that's part of the challenge here in managing some of these use cases. I guess I wanted to ask David. I know Ashley had mentioned coordination and collaboration between the scientific community and SpaceX. Could you provide any insights into that, and how that process works, or lessons learned for the folks listening?
Yeah, that was great. And by the way, Ashley, if you ever are teaching a class on this stuff, I would gladly sign up. That is so interesting. But we do a number of things. So our spectrum, the spectrum that we're allowed to use, actually is adjacent to a radio spectrum band. in the like 10, 11 gigahertz range. And so one of the things that we did right off before we ever even started operating is we got had an arrangement with the radio astronomers who were using that band, where we've essentially 250 megahertz of our adjacent band that is theoretically under our license that we have access to, we've essentially used as a guard band, and we just don't use that band in order to be able to, because the radio astronomy readings that they're doing in that band are so sensitive that if we're operating immediately next to it, that there could be bleed over. So in order to avoid any of the bleed over, we gave up 250 the megahertz in order to be able to give enough space to be able to have that. And we're constantly in discussions with the radio astronomers. One of the things that also resonates to me about what Ashley was saying is you say radio astronomers, there's not one group. There's all over the world, a lot of different interests, a lot of different use cases. It's all of this is heterogeneous. And so there's a lot of different discussions, and it's constantly ongoing because we're constantly evolving our technology. But also on the radio astronomy side, the technology is constantly evolving. So you can't just strike one deal and say you're done. This has to be an ongoing conversation, and we're constantly learning from each other. And as our services are evolving, we're having the conversation. We're trying to be as transparent as we can about what we're doing and try to learn as much as we can about what's evolving on the radio astronomy side in order to be able to make sure that the arrangement we have is always putting, I mean, with a 250 megahertz guard band, that's great and that protects the service, but that also means that there's now a huge chunk of spectrum that's basically going unused. So is there a way to think about, again, to the highest and best use, is there a way to think about that as we look ahead going forward? And, you know, the only way to do that, as Peter said, is to continue to talk and learn. The other one that got a lot of attention, we got surprised actually on our first launch that our satellites went up and they're reflective. And it means that we are so low, we operate so low and so close to the atmosphere that you could see them. And we didn't know that that was coming. And so that was troubling. I think that, you know, the first couple of launches wasn't such a big deal and could be worked around by the optical astronomers. So not the radio astronomers, but the optical astronomers. But we saw what was coming. And so we got heavily engaged in a lot of discussions with optical astronomy groups to learn what works and what doesn't, what do they need, what are their use cases, and what can we do. And we've taken a number of steps to mitigate how we operate now. And so, for example, like our satellites, we turn them on their side when we first deploy them so they don't reflect in the same way. For a little while, we were putting visors on them to block the sun to prevent reflectivity. But this is also an ongoing discussion because the optical astronomy, the technologies on that side and what they're trying to do on that side is constantly evolving as well. And so, and as we're developing the new our new systems and our new satellites, we went from kind of bolt on new ideas and like figure out how to go, that as we're moving forward, we have this in mind. And so we have like reflectivity mitigation by design as opposed to a bolt on idea at the end. But nobody knew this was coming. You can look through all the discussion ahead of our launch. Nobody said anything that this was a possibility. And so this is one of those things that we have to learn from experience. And because we're essentially first movers on a lot of this, we are spending as much time as we can and as much engagement as we can to try to learn and potentially, we hope, set best practices. Another thing that we've learned actually that was kind of counterintuitive is that lowering your satellites closer to the Earth actually is better for astronomers, for optical astronomy. Because when you're further up, you're moving across the range of the sky, your view of the sky much slower. The closer you get, the quicker you move. So actually lowering your satellites is actually much better. It's not something you necessarily would have thought of, but as we started working on it, it's one of the things that together, you know, with the astronomical community, that we were able to kind of discover this. And we've been lowering our satellites for a number of reasons, but that's one of the benefits that we've been getting from it. And again, we're hoping that these learnings, we try to make them public, we try to publish what we're learning and help all the other operators learn as well as we go forward.
Yeah, that's great. And you know, it goes back to that model of trying to understand both sides, you know, trying to develop trust relationships, which are, you know, critical when it comes to developing sharing approaches. I want to take a minute and pivot now, talk a little bit about the international domain. And so Alexandre, and your position as chief of the Space Services Department in the Radiocommunications Bureau of the International Telecommunications Union, or ITU, in Geneva, you are acutely aware of emerging global challenges with respect to spectrum. Clearly, the growth of NGNSO satellites, which orbit the globe every 90 minutes, create new challenges, but also new opportunities to explore new solutions. I wanted to ask if you could provide your perspective from the ITU, what you see evolving internationally, and with regards to the opportunities and challenges for sharing spectrum with regards to space.
Yeah, sure. Thank you, Scott, and thank you for the invitation. Well, what we see is 4 main trends. Some of them are very well known. Some others are maybe a little bit less known from the general public. So the first main trend that we see, of course, is the advent of what we call the mega constellations, these large systems of non-GSO satellites that are going to provide broadband internet. So this mega constellation, in terms of sharing spectrum, I'm not so sure, in fact, that they create so many challenges, in the sense that there are currently many projects, but let's be clear, in my view, it will be more the market than the access to spectrum that will decide who is successful. And I'm not so sure that the market will allow all projects to be successful. But at the end, I don't really think it will be a SpectrumX that will decide on who will be successful. I really believe this will be the quality of the service offering, and as often, the end user and the customers that will decide on that. The impact, however, on sharing from these mega constellations is that definitely they need more sophisticated tools to develop methodology and get results how to share between themselves. However, and this is understandable because in the time of the geostationary satellites, in fact, sharing is was very easy in a way. An Excel spreadsheet was enough to make the computations to share. Now it's not the case. You need to simulate the constellations to check the percentage of time of interference and so on. But again, this is a question of improving the tools. As you know, we are also living in a period where a number of improvement in the software industry is coming, and so I don't really believe it will have a major impact. The second big trend that we see is, of course, and is also well known, the surge in small sats, but this time not really in constellations. Small sats that are launched by small companies, 1 or 2 at a time, maybe sometimes a small group of 4 or 5. So these kind of systems are certainly emerging, providing a lot of different solutions, from Earth observations to IoT, but also signal intelligence. And Ashley was mentioning, you can even use it for scientific purpose. You have seen probably that NASA has launched a small sat to accompany a probe on Mars to check the health of the probe. So there are many solutions. Here again, I don't really believe that sharing is really an issue because there are quite a lot of bands available. The spectrum requirements of these systems are not so high. It's not like the constellations that want to provide broadband internet. Very often, this small sat needs smaller bandwidth to get their mission done. And very often as well, these small sats rely, in fact, on the transmission of data that they collect from the space. Not necessarily, they are not necessarily designed for communications. The third trend that we see, and that is a little bit less known, is a surge in national small geostationary satellites. So a number of countries are now considering the importance of the space industry for their development, for their economic development, and they want to launch a national project, a national program of satellites based on a GSO. As you may have seen in the market, there are now small GSOs that are available for about half to 1/3 of the price of a GSO. And this becomes very interesting for these countries. This is a little bit more challenging because the GSO orbit is quite crowded. In some area, it's almost close to full. And the point also is that these national programs are not really based on economic reasoning. They are not necessarily economically viable because they are designed as a strategic asset or as a development of a national capacity for the economy. So they may not, they may prosper, or they may even be launched without necessarily an economic, I would say, an economic business plan behind it. So it means that these number of projects may also have a kind of difficulty to actually get access to the GSO spectrum. So depending on the area where they want what they want to cover, they may get some difficulties, and we may have to see how to make some room for them. The last one is quite well known in the, well, it's making the headlines, but it's still a nascent one. It's really the commercial space exploration. So up to now, space exploration was mainly the realm of space agencies. Now we are seeing more and more commercial companies entering into this field, even if it is still, I would say, under the umbrella, under the auspices of the space agencies, because still governments are leading the space exploration, but most of the governments are willing to offer a room for commercial industries in the new space exploration. So you have companies willing to go to the moon together with the, I would say, under the auspices of the Artemis project. And also you have now some companies planning to mine asteroids or to go to Mars. And you have even some companies that we have seen looking for spectrum to develop, I would say, a kind of GPS, but around other celestial bodies. So this is a little bit of science fiction, I must say. This is probably not going to happen very quickly, but there are ideas like that. So for that, I would say, in terms of sharing and of spectrum access, there may be an issue if this becomes really a flourishing market. So we don't know yet because this is very nascent, but if really there is a lot of commercial development for space exploration, then we will have to probably identify new spectrums through the traditional means of having new allocations through the World Radio Conference. Because currently all the spectrum allocated for the space exploration was done on the basis of the requirements of the space agencies. And they were very, I would say, cautious to use their spectrum very efficiently and to minimize the spectrum requirements as much as possible. I feel that if there is really a development of the space exploration, especially if there is a development of the mining industry in the outer space, there will be a growing need of additional communication links and therefore additional spectrum requirements. But that is more on the longer term, probably in the next 8 to 10 years. So in summary, that's the 4 trends that we see.
Well, it looks like you got some interest here from the other panelists, and I'll go to David here, and I suspect that Ashley is going to have a comment about the radio quiet zone in the lunar environment, the shield zone of the moon. But wanted to hear David's thoughts first.
Hey, yeah, and I will try to be quick. I want to hear what Ashley has to say too. The breadth of what Alexander was talking about is a little overwhelming. So I just wanted to zero in on something at the very beginning, talking about whether or not there's enough spectrum for all the different operations that are coming in. And I think Alexander's right. I think that's right, that there is enough spectrum for everybody if we all get along. And I think the if we all get along is really, really the important part. And when we think about policy, the way that it works for the kind of spectrum that we're using for our next generation satellite systems, as I was mentioning earlier, it's all shared. Basically, the requirement is that we need to negotiate amongst ourselves on how to resolve any interference problems. that means that all of our policy, as we think about our policy, is setting the stage for those negotiations. It's setting the table for when you're starting to talk operator to operator of how can we get our systems to work together. And it's the regulations then drive what are the incentives and who has an incentive to concede anything, or how do you work together. And as Alexander was saying, there's technologies that's evolving that's making it easier and easier to be able to coordinate, or I shouldn't say easier, but possible to coordinate in new ways. But those cost money, and they cost money in R&D, they cost money in time, makes your satellites more complicated. And so you need to have policies that drive you to drive operators to want to invest in getting along. And so I think Alexander's right that there is enough spectrum for everybody and that it can be driven by the market, but that is contingent on that the policies actually encourage all operators, everybody, to sit down at the table and work together and to actually invest in improving their systems in order to be able to share, because otherwise the incentives go the other direction. Because otherwise, in a shared environment, your incentives are actually to build a system that can't share well, because then you can bump out all your competitors by having a bad system, and it saves you money by doing so. So I think that's the key, is to get this to work. You have to be thinking out what are the incentives and how are we driving operators to do the right thing.
And I want to circle back to that question in just a moment to you, David, about incentives and the challenges and efficiency, but I did want to give Ashley a chance to respond here.
So the shielded zone of the moon is really interesting, but I was actually going to comment on something similar to what David said. I was really happy to hear what Alex commented on, that the computer models are really improving, but one of the challenges I think we've seen with sharing is the impact of aggregate emissions. So that's kind of what David was referring to, how do multiple different systems all contribute together to sort of an aggregate level of interference or an aggregate signal. And so just a concrete example of this is the steps that he described for the SpaceX system to actually meet the radio astronomy recommendations does permit about 2% of observations from a single operator to cause interference 2% of the time, because they said, okay, no one's perfect, we permit about 2%. And so you can have two operators each causing 2% of the time interference, but the international recommendation says, the aggregate of all operators should be 5%. So then you can do the math and you get right to the point David was making. What happens when the third operator comes in, when two of them are already providing 2% interference? What is that aggregate interference? And, that really needs to be included in our model. So that's a very important, line of effort to make sure that models include that aggregate, but then also what David was mentioning about incentives. So just wanted to add that point in.
Great. So thanks, Ashley. So David, back to your comment about the rules and sharing. I have heard that there's building of efficient systems sort of is a way to inefficient systems is potentially a way to game the system, and you were sort of leaning on that a minute ago. Could you provide some more insights about what you mean there, and how we get to a place where we've incentivized through policy or other mechanisms to build efficient systems so that we can get the best and highest use from the spectrum?
Yeah, sure. I guess since this is it's in a law school, I will use a torts example. Is what I think about a lot of times is that when you're developing the systems, you may have an incentive to become if it's shared spectrum and everybody is using essentially the same plot of land. We're all in the same place, and we all have to get along. I may have an incentive to build as much as I can, but then become the eggshell plaintiff, right? Be as sensitive as I possibly can to interference. So that way, if anybody else comes later, or even somebody is coming at the same time as me, that I come in and I'm able to turn around and then scream and yell that, oh my gosh, they're causing me interference. Now, the question is, and this I think should be a question that's not just in space, actually. I think that is spectrum across every facet of this. The question should always be, when someone's saying that they can't share or they're specifically subject to interference, is the question because the physics requires that? And a lot of times it is because of the physics, right? It's if you're operating like we do, referencing earlier the 12 gigahertz, we're operating at such low power that there's physics there that it's just like we get interference just if there's higher power, we're at such low power, it just does it. But is the question always physics or is it the technology? And is it that you didn't invest in the technology that allows you to be able to coexist? And I think that's one of the things that policymakers need to be able to suss out when they're looking at these issues that are coming up is, are the people who are complaining about interference and they're saying that they can't share or they can't coexist, is it because of physics? And sometimes it is, or is it because I built a system? And there's two reasons. Now, I may have built a system because I just didn't want to spend the money on one that can share, but I may have built a system intentionally sensitive to interference because in a shared environment, the more sensitive I make myself and the more I make it that I'm not able to get along with anyone, the more that I will be able to claim the territory for myself. Is if all the rule says is you guys all negotiate amongst yourselves and figure this thing out, and then the regulators are going to step back and we're only going to come in if there's interference. My incentive is now build a system that claims as much territory for myself as I can. And so one of the things that I think policymakers can do, and we've actually have a petition in front of the FCC on this, is actually reward operators who meet some level of efficiency. And I know there can be a fight over what efficiency means, and putting that aside, and we can fight over what efficiency means, but come up with some sort of metric of what efficiency is and reward the operators with more spectrum or some, there's different ways to do it, but reward the operators who are actually investing in the systems that meet the metrics for efficiency that we decide on. And then you can kind of flip the incentives around. Instead of a race to the bottom where everyone wants to build the least efficient system to claim territory for yourself, that everybody now actually wants to build the most efficient system in order to be able to reap the regulatory rewards that are put in front of you. So you can have carrots and sticks put in there.
Great. And I saw, Peter, you were nodding your head as David was talking. What you have some thoughts there? And I guess also, are there other incentives for sharing that we might consider to help move forward?
Well, David had raised very good points, and I just wanted to make sure I couldn't clap. Want to put that emotion to clap, or cheer dramatically for his very thoughtful thoughts. And but one other one, what brought to mind is there's actually language in the Spectrum Pipeline Act from a few years ago that has a prize authority for the Department of Commerce to award prizes for spectrum efficiency. And this seems like a great area to do that. Problem is it's not funded. And one of the requirements for that prize to kick in is for the FCC to, I think, come up with a definition of efficiency. And so it might, create an incentive to be efficient, that way by, putting in some money. But really, I mean, it's all comes down to cost, right? And what is their cost calculations? And so if there's transparency requirements or negotiation requirements, and I think if the regulators step back and only, say, we'll come in if there's a dispute, but if there is a dispute, the question is, who has the burden, right? Who has the burden to show, that when my model is correct, and their model's not correct, and how do you balance the interests there? So none of those processes have ever been established. It's basically ad hocery, case by case, a mess, and like I said, in the C-band, it seemed to work relatively well, comparatively well, because more interests were aligned than not, and they seemed to get along. But if the regulators kind of just say, we don't know ex ante before the fact, a lot of this stuff, and really the problems are going to come up ex post. We'll be there ex post, and when it does happen, here's the burden on the various parties. The person who says that, like, they're going to be interfered with will have to show that they've built, for example, the best state-of-the-art receiver in their system, and are not, kind of wasting spectrum with sloppy receivers. That would be an example. But I don't know. David makes a lot of great points. That's why I shake my head vehemently, up and down.
When as we talk about this, yeah, Alexandra.
Yeah, just maybe two points. In my view, in the C-band, things were eased by the fact that there were a lot of financial incentives to repack the spectrum from the satellite point of view. I mean, the idea was that the satellite industry was not simply, I would say, called to improve their spectrum efficiency. They were clearly rewarded to do so by quite a lot of money, about $9 billion. So this is a major incentive, and generally, many people get more more agreeable to think about such things when they see such an incentive, especially for the satellite industry. If you look at what is the turnover of a satellite operator, the money that was engaged was really appealing. The second part is that, at least on the international side, there is a kind of balance between the right of the, I would say, sensitive incumbents and the newcomers, or the more efficient newcomers, is that indeed the newcomers have to protect the incumbents, but not at all costs. They have to. There are limits to which the protection is due, but also when there are a dispute on the level of interference, ultimately, this is the incumbent that has to be able to prove that it is interfered. And it has to be able to produce measurements to show the actual interference. So if your interest is simply to increase your sensitivity, be sure that you have the means of measuring it. Because if you try simply to block a competitor using the technical regulation, then it may not be so easy, because you will need to spend a lot of money building a lot of detailed monitoring stations just to ultimately maybe try to block a new entrance, which probably you will not even succeed in. So this balance was established in order to avoid the kind of difficulties that have been explained by David, for which I agree. Then what David is proposing is a step further, not only trying to have a balance between both incumbents, but also rewarding those the most efficient one. And I think it's a great idea. The main difficulty up to now is that I think collectively the community has never been able to define what is the most efficient use or the most efficient system in a certain band. And this was the main. This is the main missing point in my view. Thank you.
Great. So we've been getting a number of questions coming in. So I'm going to move into sort of the open Q&A time here. I want to encourage the panelists that if you click on the Q&A button, you can see the questions that have come in. Feel free. I saw Alexandre has answered in a text response. But what I will do is give you the opportunity, if there's a question in there you would like to answer specifically rather than me deciding, feel free to raise your hand, and we can do that. And of course, following the wiser rule here is that we start with a student question. And so I understand that we have a CU student, Taylor Hartley, on hand to ask the first question. And it looks like Keith is up at the podium. So I think I'll have Taylor coming in.
All right, hello. That was so much fun. Thank you so much. My name is Taylor Hartley. I am an MBA student here, and I have a background in intelligence, surveillance, and reconnaissance. So my big question is, what does security look like in these non-terrestrial networks and a shared spectrum? Are there more concerns, less, and what's happening?
A great question, and there's definitely lots of discussion about cybersecurity with regards to space systems. Alexandre, you want to comment on that?
Yes, thank you. Maybe the first answer is that very often the weak point of the satellite systems are in fact the terrestrial part of the satellite system. So the ground segment of a satellite system is the most vulnerable to cyber attacks, simply because it is also the easiest one to get access to. Cyber attacking a satellite system, it's certainly a satellite itself in space. This is certainly possible, but currently it requires a lot of technology that is not really available to I would say, a large number of entities or governments. What is much easier is indeed to hack the ground system, the transmitting stations toward the satellite, and then use it as a backdoor to the entire system. Of course, this calls for more security on this part of the satellite systems. I would say the satellites themselves, they are quite well protected to now.
Ashley?
Yeah, I just wanted to highlight, I think this is a fantastic question. And so this is something that NSF, the Directorate for Engineering, has been investing in a lot. And it's not just for the areas you mentioned in terms of reconnaissance and intelligence, but also just as we think about keeping our data secure, whether it's, your stock market portfolio or your banking or, personal communications you have with family members. So I wanted to highlight one program at NSF called Secure and Trustworthy Cyberspace. And this is, definitely looking to fund research to address those challenging scientific and engineering problems. And they highlight, that there's many components of that system that you have to consider for the security and privacy. And so, this is an active area of research. So, I think what you highlight is very important. It's going to just become an increasing area of research as we have more and more wireless devices. You have to worry with backward compatibility, with things like the Internet of Things, making sure that, the old devices are actually not easier to get hacked and then get into other, devices in your house, for example. So, this secure space, very active area of research. So, fantastic question. And, happy to point you to a number of, the research grants that we funded in this portfolio or get more information, but just wanted to say, great question and very active area.
I think there's also sort of an interesting sort of ongoing challenge, at least for a lot of the new entrants who are getting into small satellites. They, oftentimes are the ones that maybe aren't as secure, and there's a push with the challenges in space debris to have maneuverability on orbit. So to be able to have propulsion so that you can change your orbit or avoid a potential collision. However, now that once you put propulsion on spacecraft, you can change your orbit and do other things that may be more nefarious. So it creates an interesting challenge with regards to having the capabilities to maneuver, but also requiring sufficient security so that those spacecraft can't be used for nefarious purposes. I didn't know David operating. David just disappeared here. Oh, there he is. You put your hand up. That's why you moved when you put your hand up. I was gonna comment. As an operator of the largest satellite constellation, what are your thoughts regards to, I would guess, both cybersecurity and then also the increasing challenges for orbital debris?
Oh, with the debris also. Yeah, so I guess addressing security first, and I don't want to claim to be a security or cybersecurity expert. I have some passing knowledge, probably enough to be dangerous, so I should be careful. But one of the things that, just to add like one additional point to it, is these systems are global, right? And so unlike even geostationary satellite systems that could be operating in a specific region, When you're non-geosynchronous, almost by definition, not all of them, but most of them have some sort of global reach. So you're dealing with a lot of different countries. You're landing your data in a lot of different countries, and these different countries can have different laws and can have different policies and different approaches. And so just think about if you're landing in one country that says everything is very, one country is very privacy focused and says everything needs to be encrypted end to end completely and locked down and you can't even access it yourself. And the country next door says, you better make sure that you have the key to decrypt it because our law enforcement's going to want to be able to see it whenever they want. And this is one network, right? And so I think you don't have the political boundaries that you have necessary, or you don't build the network with the different kind of geographic boundaries into it. So there's by being international, you have a new complication to it and a new layer of complexity in how you're thinking about it. Fortunately, we have a team of security experts who are working and thinking about these things all the time. I'm not one of them, so I can't really speak to it, but I do know that just looking at, because I deal with the policy and looking at the policy across different countries, there's trend lines moving in privacy that conflict with the trend lines that are moving in like lawful intercept data security. And I think that there could be down the road, I think there could be tensions there that will need to be thought through and worked out. Pivoting to the space debris question, yeah, we spend, a lot of this ends up having very similar discussion to what happens with Spectrum, is like, how do you make sure that people have the right incentives? And how do you make sure that people are investing? It is more expensive, as you said, Scott, that it's like, everyone wants to have propulsion now, or should have propulsion. How do we make sure that everybody does put propulsion on their system? It's cheaper to not put propulsion onto your system. And so, but at the same time, by requiring everyone to do that, you're definitely raising the barrier of entry. So like, what are we trying to accomplish? And so there's that. One of the things that we spend a lot of time on that we think is, I guess there's two main points that I would hit on debris, and then because I know there's a lot of other topics too, one is time in orbit really, really matters. I think Ashley mentioned it earlier, of kind of the global standard of satellites should come down 25 years after they're done. I think there's a almost uniform agreement that 25 years is too long. I think as more satellites are being put up and as we're trying to use space more and more intensively, 25 years is probably too long, and we should be driving it to try to get that number down lower. How do we get people to bring down satellites or get rid of their satellites when they're done with them as quickly as possible? And I think the other component to that is altitude. The higher you are, the longer your satellite, if you have a failed satellite or you have a satellite without propulsion, the longer it takes to come down. So under 600 kilometers, it'll come down within 10 years. And so even if you have a problem, basically within a decade, that problem is gone. Once you get higher than that, it quickly becomes centuries or millennia. So as you get up to say 1,000 kilometers, you could have a satellite that if its propulsion fails, it's coming down over 800 years and through some of the highest, densest orbits you have with small debris. And so you almost have like a bowling ball crashing through junk, and you're just waiting for something to happen. And so I think what we do is we try to push our satellites as low as we can down to the atmosphere, because that way, if you have issues, they go away much, much quicker. That to us is the best way to solve it. But I mean, this is going to be an issue that we need to be thinking about as we go forward. Oh, I did have, sorry, I said that I was going to have 2 points, and I don't want to be one of those people who says 2 points and then says one. Just knowledge, one of the things, and I think this is something that maybe NSF can help us with too, is knowledge of where satellites are and where objects in space are, but where they're going to be. It's actually, because like where we operate is essentially still at the highest reaches of the atmosphere. So we're still affected by the atmosphere. And so that means that it's the uncertainty of where satellites are going. It is high. It's really hard to predict. And you would think you could map it out really easily, but we just don't have the technology right now. Mankind does not have the technology right now to have really accurate predictions of where things are going to be. So one of the things that we really should be thinking a lot about in order to make sure that space is sustainable and we can use it as intensively as we can for commercial, but also for scientific exploration, is better understandings of where things are and where they're going to be. When we know where they're going to be, you can avoid it. It's the uncertainty of where something's going to be that really raises the risk.
Absolutely. So we got about a little under 10 minutes here left in our discussion. And I wanted to give the panelists an opportunity if there's something pressing that we haven't discussed, something that you think is important for the audience to hear about. If you'd like to bring that up for a final discussion. Otherwise, I can throw out one or two more questions, probably only about one. Ashley.
I just wanted to quickly address a question that came up by an anonymous attendee to ask about experiences practicing radio astronomy as a female scientist. And what I wanted to just remark on is that, I always felt very supportive and that my gender had nothing to do with ability and was very much encouraged as an undergrad, in high school, even in graduate school. And the reason I wanted to just mention this briefly is I think one of the things that's really important for us to consider is looking to broaden participation in spectrum management, right? So we want to have a group of, technically trained, from science, engineering, law that understand the international policy that really reflects like the diversity of our nation. And so that's, something important to think about how we can move towards a workforce. There's lots of challenges that I think we see moving forward that we're not going to have the workforce that we need for all of these challenges that we've described in the past hour. So I just wanted to mention that as something that is really important. And won't say anything else now because we're running short on time, but I thought that was important.
Well, thanks for those insights. And I think, thinking about the workforce development and how do we develop the spectrum managers of the future, and what are the required skill sets and the problem solving abilities, as we see, it is evolving. It's evolving, relatively, the technology is evolving quickly, and trying to manage those challenges. So maybe to wrap up would be to hear what everybody thinks, or as we have time, about what are the skill sets for the spectrum managers of the future, and how do we attract talented people into this area, David?
Yeah, I mostly just I really wanted to what Ashley said is great and right on, and I know for people who are not familiar with these topics, this can be a lot to take in, and probably every other thing any of us said was some new issue that people hadn't thought about, and it can seem like a lot and intimidating. This is all developing. These are all new things. Nobody has years of experience on all of these different issues. I want to encourage. I know we've got a lot of students listening to this, and we really do want to bring a wealth of different backgrounds, and it doesn't necessarily have to be that you have expertise in spectrum or that you know something special about satellites or space or any of these particular issues. Enthusiasm, smarts, excitement about the issues. We can figure it out. I mean, whatever we're talking about in 2 years is not going to be the same thing we're talking about this year anyway. And so we really do bringing in more diverse viewpoints across every version of diverse. I just really, all the students who are listening, like I can't encourage that more. And I hope this all seemed accessible, and I hope there's nothing that intimidated anybody out of doing this, because I really think that this is something that is fun to get into, and you'll be at the bleeding edge of new technology and new policies. Great.
So Peter, with your 25 years of experience at NTIA, any thoughts for the students? Nuggets of wisdom going forward and getting, engaged in spectrum?
Well, I used to think it's not rocket science, but I guess it is for some areas. It is not rocket science. You fall into this, like most of us, accidentally. In my case, it happened to be the person in the office next door got a new job, so I picked up her spectrum portfolio. And that's why most people I know get into these things is accidentally. But if you just want to get into telecom generally and the satellite stuff, I mean, I've seen this stuff back in the late 90s. A lot of the stuff in the NGSOs is deja vu all over again for me. And like Alexandre was talking about, the it's going to be the market deciding these things. So, you know, I know young kids these days, because I got 3 of them, and one of them just yanked me out earlier, and I apologize for that. Didn't know the time difference, but the young kids these days, they don't decide that they're going to do something for 25 years, you know, and this is going to be my career. They're going to they want to jump from one thing to another. So it's try all kinds of different things. If you got an opportunity to work with SpaceX, sweeping floors, I'd take it, you know, and even working for David. No, I'm just kidding. I would definitely want to work for David someday, you know, if I were young, but the opportunities I think are endless. It just, you know, takes a lot of networking, you know, unfortunately, to find these little creases, because the entrepreneurship in this space, no pun intended, is incredible. I'm surprised every day.
Absolutely. I think, you know, the excitement and the entrepreneurship and the buzz is there on a daily basis. So I want to give Alexandre the last word. I also want to thank him for staying late with the time zone change coming to us from Geneva. So any final comments with regards to workforce or other items you wanted to mention before we wrap?
Well, no, I think I can simply echo the previous comments. What is really interesting in my view in this field, that it's really a mix. It's at the crossroads of various fields. So you can come in this field from various backgrounds. You can be a lawyer, you can be a policy analyst, you can be also an engineer, or even a scientist. We need all of that. And nobody is too much, I would say. So we really need a diverse background to make a good use of spectrum for our fellow citizens. So without sound spectrum engineering, without sound scientific research on the use of radio spectrum, we cannot build progressive policies that will benefit the society. But similarly, if we stop at the level of spectrum engineering, if we do not transfer this information and the wealth of information to the political level and to the people that will decide the best value that we can use from spectrum, then we cannot neither reach the entire components of our societies. So really, every field is called to act in the spectrum policy domain, and this is this is increasing because more and more applications now of our daily life relies on radio. There are less and less activities where you can say there is no radio involved in this activity. So yeah, I think everybody should should consider making a contribution to it, and certainly this would be very welcome. Thank you very much.
Thank you, and I want to thank all of our panelists for the time and effort they put in, their thoughtful comments and participation here. So and making this an excellent opportunity to have some discussions about ongoing and emerging trends. So with that, I think we're wrapping up the panel, and I'll turn it back to Keith in the law school.